In this video, we are going to discuss about inductance and capacitance. A wire of certain length, when twisted into a coil, it becomes a basic inductor. If the current is made to pass through an inductor, an electromagnetic field is formed. A change in magnitude of the current changes the electromagnetic field. Increase in current expands the fields, whereas decrease in current reduces it. Therefore, a change in current produces change in electromagnetic field, which induces a voltage across the coil according to Faraday's law of electromagnetic induction. The unit of inductance is Henry and it is denoted by the letter H. By definition, inductance is 1 Henry when current through the coil changing at the rate of 1 ampere per second induces 1 volt across the coil. The symbol of inductance is shown in the figure. The current voltage relation is given by V is equal to L into di by dt, where V is the voltage across the inductor in volt and I is the current through the inductor in amps. We can write the above equation as dt is equal to 1 by L into V dt. Integrating on both sides we will get, and for dt the lower limit is 0 and upper limit is t, and on the right hand side 1 by L into integral V dt. Integration will result in I of t is equal to 1 by L 0 to t V dt plus I of 0. From the above equation that the current in inductor is dependent upon the integral of voltage across the terminals and initial current in the coil, that is I of 0. The power absorbed by the inductor is P is equal to V into I. V is equal to L into di by dt. Substitute this, the equation becomes L into I into di by dt. The energy stored in the inductor is W is equal to 0 to t P into dt. So substitute the above equation here and it results the energy stored in the inductor is given by L into I square divided by 2. The induced voltage across the inductor is 0 if the current through it is constant. That means inductor acts as a short circuit to DC. A small change in current within 0 time through an inductor gives an infinite voltage across the inductor, which is impossible. In a fixed inductor, the current cannot change abruptly. The inductor can store finite amount of energy even if the voltage across the inductor is 0, and a pure inductor never dissipates energy, it only stores it. That is why it is also called non-dissipative passive element. However, physical inductors dissipate power due to internal resistance. Capacitance. Any two conducting surfaces separated by an insulating medium exhibit the property of capacitance. The conducting surfaces are called electrodes and the insulating medium is called dielectric. A capacitor stores energy in the form of an electric field that is established by the opposite charges on the two electrodes. The electric field is represented by the lines of force between the positive and negative charges and is concentrated within the dielectric. The amount of charge per unit voltage that is capacitor can store is its capacitance, denoted by the letter C. The unit of capacitance is farad and it is denoted by F. A capacitor is said to have greater capacitance if it can store more charge per unit voltage, and the capacitance is given by C is equal to Q by V. We can write the above equation in terms of current as I is equal to C into dV by dt. current is equal to dq by dt, where V is the voltage across the capacitor and I is the current through it. And from this above equation, rewriting it results dV is equal to 1 by C into I dt. Integrating both sides, we have integral 0 to t dV is equal to 1 by C integral 0 to t I of dt, which results V of t is equal to 1 by C integral 0 to t I of dt plus V of 0, where V of 0 indicates the initial voltage across the capacitor. From the above equation, the voltage in a capacitor is dependent upon the integral of the current through it and initial voltage across it. The power absorbed by the capacitor is given by P power is equal to V into C into dV by dt. The energy stored in the capacitor is integral 0 to t P of dt, which results the energy stored in the capacitor is given by half CV square. The current in a capacitor is 0 if the voltage across it is constant. That means the capacitor acts like open circuit to DC. A small change in voltage across the capacitance within 0 times gives an infinite current through the capacitor, which is physically impossible. In a fixed capacitance, the voltage cannot change abruptly. The capacitor can store finite amount of charge even if the current through it is 0. And a pure capacitor never dissipates energy but only stores it. That is why it is called non-dissipative passive element. However, physical capacitors dissipate power due to its internal resistance. Thank you.